So here we have a question on vectors. We're told that line L1 has this Cartesian equation and line L2 has this parametric equation, where this t is a scalar parameter. We've been asked to show that L1 and L2 lie on the same plane. So the first thing I would do here is to write them both using column vectors. So for L1, we'll say that R is equal to the position vector, which is the negative of each of these. So 1, -1, and +4, plus lambda, and then the direction vector would be each of these. So 2, -1, +3. And then for L2, I will be equal to, we've got 1i, 0j, and 3k. So 1, 0, 3, plus t, 1, -1, and 2. And to show that they lie on the same plane, we need to find the general position of each of these lines. So for L1, we'll have the x component of 1 plus 2 lambda, the y component of -1 minus lambda, and the z point of 4 plus 3 lambda. For L2, we'll have 1 plus t minus t and 3 plus 2t. Now, if they lie on the same plane, then they must intersect. So what we need to show is that they do intersect. And if they intersect, then their x, their y, and their z values will be equal for some point where L1 equals L2. So what we need to show then is that 1 plus 2 lambda, the x value of L1, will be equal to the x value of L2, 1 plus t. The same for the y points, and the same for the z. So now what we can do is find lambda and t using simultaneous equations with these two, and then we can check that lambda and t works in our third equation. So therefore, for our x values, 2 lambda minus t will equal 0. For our y values, lambda minus t will equal -1. Then we can find lambda and t using the equation solver on our calculator. So if we go to menu, we want 1 and then 2 unknowns. Our x would be lambda, so 2, -1, constant of 0. Then we'll have a coefficient of 1 and -1 with a constant of -1. So lambda will be equal to 1 and t will be equal to 2. So now we need to show that this statement is true using these values of lambda and t. So 4 plus 3 lots of lambda should equal 3 plus 2 lots of t. We get 7 does equal 7. So what we say is, the two lines intersect, and therefore they lie on the same plane. Okay? Part B, write down the vector equation for a plane containing L1 and L2. So we're going to use a parametric equation for a plane. We'll say that for plane pi, we need two direction vectors plus a position vector. And from our question, we could use either of these as a position, and here are our two direction vectors. So the equation of our plane would be 1, -1 and 4, the position, plus lambda lots of 2, -1 and 3, plus t lots of 1, -1 and 2. And this would be the equation of our plane. For part C, find to the nearest degree the acute angle between L1 and L2. So what we need to find is this angle here, where cos theta, if this is theta, will be equal to a direction vector of L1 dotted with direction vector of L2, which is here, divided by the product of a magnitude of each direction vector. So we'll dot these two together. We get 2 add 1 add 6. So cos theta will equal 9 over the product of these, which is 2 root 21, then we'll take the arc cos of both sides, so theta will equal 10.9 degrees. To the nearest degree, this is 11 degrees. Okay?